In this part of the syllabus, we are introducing a new term, chemical affinity. Chemical affinity and thermodynamic functions, how it is connected to, related to other thermodynamic functions. Then we have to see effect of temperature and pressure on chemical equilibrium. That would lead to the derivation of Van Hoff's reaction isochore and Van Hoff's reaction isothane. So this is a very important topic, and these are frequently asked questions. Okay. So let us begin with the new concept, chemical affinity, and its relation with other thermodynamic functions. Okay, so here we are introducing this new term, chemical affinity, which is represented by the symbol AF, and another new term, extent of reaction, which is represented by the symbol theta. Okay, so let us see what is chemical affinity. It is the rate of decrease of free energy with extent of reaction at constant temperature and pressure. So when a reaction proceeds, how the free energy decreases, or to what extent the free energy decreases as a reaction proceeds. Okay, so it is the rate of decrease of free energy gives free energy G with the extent of reaction at constant temperature and pressure. That is chemical affinity. It is represented by the symbol AF. AF can be expressed as minus dou G by dou theta at constant temperature and pressure. That is the rate of decrease of Gibbs free energy with respect to the extent of reaction at constant temperature and pressure, and this is equal to minus delta G. Okay, so the change in Gibbs free energy during a reaction. So chemical affinity AF can be equated to minus delta G. AF is equal to minus dou G by dou theta at constant temperature and pressure, which is equal to minus delta G. This is equation 1. And for any chemical reaction, the free energy function depends on temperature, pressure, and concentration of the reactant species, right? Free energy function G would depend on temperature, pressure, and concentration of reactants, which in turn are the measure of the progress of the reaction. So when a reaction proceeds, by checking the concentration of the reactants or the concentration of the newly formed product, we can find out the extent of reaction or the progress of reaction. So actually the extent of reaction can also be related to concentration, right? So for a chemical reaction, the free energy function, the decrease in free energy or change in free energy, that would depend on temperature, pressure, and also on concentration of the reacting species. So we can write the free energy G for a chemical reaction as a function of temperature, pressure, and concentration of reacting species, or the extent of chemical reaction theta. So G can be expressed as a function of temperature, pressure, and theta. So we have obtained free energy G as a function of temperature, pressure, and theta. Now next what we have to do, we will find the total differential, right? So total differential dG is equal to dou G by dou T with respect to the first function, right? First variable. Dou G by dou T at constant pressure and theta, at constant pressure and theta, dt plus dou G by dou P. Dou G by dou P at constant temperature theta dt plus dou G by dou theta at constant temperature pressure d theta. So we have just found the total differential, the change in free energy with respect to each of these variables. Okay, that is equation 2. But we know that dou G by dou T at constant theta and pressure is equal to minus S. Do you remember from this equation we got this expression? We know dG is equal to VdP minus FdT, right? dG is equal to VdP minus FdT. When pressure is constant, this VdP term becomes 0. Then we have only dG is equal to minus FdT. So when we take dt to the left side, we get dou G by dou T. So constant theta and pressure will be equal to minus S, right? dG was equal to minus FdT, and when we express it as dou G by dou T, it became equal to minus S. And from the same expression, at constant temperature, this dt term will be equal to 0. So we have only VdT. dt is equal to VdT. And when we take dt to the left side, we get dou G by dou P. At constant temperature, theta is equal to volume. So we have both these expressions, dou G by dou T at constant theta pressure is equal to minus S, and dou G by dou P at constant temperature theta is equal to volume V. And we have already learned this expression for chemical affinity AF is equal to minus dou G by dou theta at constant temperature and pressure, right? Rate of variation of free energy with respect to extent of reaction is equal to chemical affinity. So we have taken negative sign here. So dou G by dou theta at constant temperature is equal to minus AF, which is equal to delta G. Okay. So now have a look at equation 2. So we have this same dou G by dou T at constant pressure theta, right? Dou G by dou T at constant pressure theta is equal to minus S. So we can substitute minus S instead of this term, and dou G by dou P at constant temperature theta is equal to V. So we can substitute this V here, and now we have dou G by dou theta at constant temperature and pressure, which is nothing but minus AF or delta G. So we can substitute for all these terms in equation 2, and equation 2 becomes this dg. dg is equal to, instead of this term we can write minus S. So minus F dt, minus F dt plus, instead of this term we can write volume V. So we have V dt minus same because this is minus AF, right? Dou G by dou theta at constant temperature pressure is minus AF, then we have d theta. So minus AF d theta, that is equation 3. So here we have found how the chemical affinity AF is related to Gibbs free energy G, right? dg is equal to minus S dt plus v dt minus AF d theta. Remember this equation. Similarly, chemical affinity AF can be related to other thermodynamic functions as well. Now let us see the relation between work function and chemical affinity. What is work function? It is nothing but Helmholtz free energy A, right? So we are going to see the relation between Helmholtz free energy or work function with chemical affinity. For that, let us begin from the basic equation G is equal to H minus Ts, and H can be written as internal energy plus PV. Normally we use the symbol U. Here I have used the symbol E. This is why you can substitute it for U. Okay. So we have this expression G is equal to E plus PV minus Ts. And what is E minus Ts? It is nothing other than Helmholtz free energy A, right? Helmholtz free energy A is equal to U minus Ts or E minus Ts. So instead of E minus Ts, we can substitute A. So we have G is equal to A plus PV. Let us rearrange this equation to find out A, and A is equal to G minus PV. G minus PV. Okay. And now imagine there is an infinitesimal change in A, Helmholtz free energy A. Then there will be associated changes in Gibbs free energy and the pressure volume terms, right? So dA will be equal to dG minus PdV minus PdT. Let that be equation 4. Now we have to substitute equation 3 in equation 4. Try to find out equation 3 from the previous video or your notes. Equation 3 related dg, right? dg is equal to minus S dt plus V dt minus AF d theta, right? Minus S dt plus V dt minus AF d theta. So dg was equal to this term. So instead of this dg in equation 4, we can substitute equation 3 minus S dt plus V dt minus AF d theta, and then we have minus PdV and minus VdT terms remaining in equation 4. So we get dA is equal to minus S dt plus V dt minus AF d theta. These terms corresponds to dg from equation 3, and then the remaining terms minus PdV minus VdT. And these terms VdT we have both positive and negative signs. It can take out. So we have dA is equal to minus S dt minus PdV minus AF d theta. Okay. Now assume temperature and volume are constant. So this equation was modified to dA is equal to this dt term becomes 0 and dv term becomes 0. So what remains here? Only minus AF d theta, right? So we have dA is equal to minus AF d theta. Let us take this d theta onto the left side. So we get dA by d theta at constant temperature and volume, right? dA by d theta at constant temperature and volume is equal to minus AF. And we know minus AF is equal to delta G from the first equation itself, right? So the relation of Helmholtz free energy or work function with chemical affinity is dA by d theta. Variation of work function with respect to extent of reaction at constant temperature and volume is equal to minus AF. This in turn is equal to change in this free energy. Now let us see how enthalpy is related to chemical affinity. The relation between enthalpy and chemical affinity. Enthalpy H is equal to G plus Ts. From the equation G is equal to H minus Ts, we just rearrange it to find out H. H is equal to G plus Ts. Now for infinitesimal change in H, the equation can be modified as dH is equal to dG plus CdH plus SdT, right? dH is equal to dG plus CdH plus SdT. And now for this dG term, we can substitute from equation 3. And dG from equation 3 is minus SdT plus VdT minus AF d theta, right? So this equation dH is equal to, instead of dG, we have introduced these three terms. dH is equal to minus SdT plus VdT minus AF d theta, and the remaining term TdS plus TdS plus SdT. And these plus and minus SdT terms cancels out, and we have dH is equal to VdT minus AF d theta plus TdS. So we will need this term only here on the right hand side. So we are assuming pressure and entropy are constant. Okay. So constant entropy and pressure, this ds becomes equal to 0 and dT becomes equal to 0. So we have dH is equal to minus AF d theta. dH is equal to minus AF d theta. Taking this d theta term on the left side, we get dou H by dou theta at constant entropy and pressure is equal to minus AF minus chemical affinity, which is equal to delta G. So rate of change of enthalpy with extent of reaction at constant entropy and pressure is equal to minus AF, which in turn is equal to delta G. Now we are going to check the relation of internal energy with chemical affinity. So we begin from the same equation, G is equal to H minus Ts, and instead of H we can introduce the internal energy term here. So G is equal to E plus Td minus Ts. From that we can find out internal energy E, because we are going to check relation of internal energy and chemical affinity. So E is equal to G plus Ts minus Td. Just a rearrangement between these terms and these terms. Okay, so E is equal to G plus Ts minus Td. Now what we have to do, we have to check what happens when there is an infinitesimal change in internal energy E. So D is equal to dG plus TdS plus SdT minus TdV minus dV. We have to differentiate each and every term. Okay. And now we can substitute from equation 3 the value of dG, right? Value of dG is minus SdT plus VdT minus AF dT. So our equation for internal energy change, dV becomes equal to, instead of dG we have minus SdT plus VdT minus AF d theta plus all these remaining terms plus TdS plus SdT minus TdV minus VdT. And here we have VdT plus and minus VdT terms plus and minus SdT terms. And they cancel out. So we have D is equal to minus AF d theta plus TdS minus TdV. And we need only these terms here. So we have to assume entropy and volume are constant. So ds and dv becomes equal to 0. And we have d is equal to minus AF d theta. Rearranging this equation, we get dou E by dou theta at constant entropy and volume is equal to minus AF, which is equal to delta, right? So So this is the radiation of internal energy with respect to extent of reaction is equal to minus air. Okay. So from all the above expressions, we can conclude that Gibbs free energy G is a function of temperature, pressure and theta. Work function or Helmholtz free energy A is a function of temperature, volume and theta. Enthalpy S is a function of entropy, pressure and theta. And internal energy E or U is a function of entropy, volume and theta. Now we can find out change in free energy dG, change in Helmholtz free energy dA, change in enthalpy dS or change in internal energy dE. Okay, so dG, change in internal energy, dG will be equal to the total differential we can find out. dG is equal to dou G by dou T. We have to differentiate with respect to each of these variables, right? So dG is equal to dou G by dou T at constant pressure theta dt plus dou G by the second term, right? Dou G by dou P at constant temperature theta dt plus dou G by dou zeta at constant temperature pressure d zeta at equation 5. Similarly, we can find out the total differential for Helmholtz free energy A. dA is equal to dou A by dou T at constant volume theta dt plus dou A by dou V. Dou A by dou V at constant temperature theta dt plus dou A by dou zeta. Dou A by dou zeta at constant temperature volume d zeta. That is expression for change in Helmholtz free energy dA. Equation 6. And the total differential dS will be equal to dou H by dou S at constant pressure theta ds plus dou H by dou P. Dou H by dou P constant entropy theta dt plus dou H by dou zeta at constant entropy pressure d zeta. Okay. Similarly, change in internal energy dE will be equal to dou E by dou S at constant volume zeta ds plus dou E by dou V at constant entropy zeta dV plus dou E by dou zeta constant entropy volume d zeta. Okay, so these are the expressions for change in Gibbs free energy, Helmholtz free energy, enthalpy and internal energy.